Chapter 5 Electromagnetic Induction. In Form 2 on the chapter on magnetic effect of an electric current, we observed that a current carrying conductor generates a magnetic field around it. This discovery by Hans Oersted in 1820 opened a whole new vista for research, and what many wondered is whether the converse can be true. Could a magnetic field induce current in a conductor? And it wasn't long, as one can imagine, before new discoveries were made. In 1831, Michael Faraday in London and John Henry in New York independently discovered that indeed the converse was true. A changing magnetic field can, under special conditions, induce current in a conductor. This is called electromagnetic induction, a phenomenal discovery that ultimately led to the birth of electricity. Let us see electromagnetic induction in a straight conductor. What we have is a conductor between two arms of a horseshoe magnet. The two ends of the conductor are connected to a galvanometer by means of wires. When the conductor is moved downwards, the galvanometer deflects, indicating that a current is induced in the straight wire. When moved upwards, the galvanometer is deflected momentarily in the opposite direction, indicating that current is flowing now in the opposite direction. If moved parallel to the magnetic field, the galvanometer shows no deflection, indicating that no current is induced. When held stationary in the magnetic field, the galvanometer again indicates that no current is produced. We can also induce current in a circular coil of copper wire. We connect its two ends to the two terminals of a sensitive galvanometer with a scale indicating 0. Note that this circuit has no source of electricity. We take a bar magnet and move it swiftly towards the coil with the north pole facing the coil. We observe a deflection in the galvanometer when the magnet is moving, indicating that current is set up in the coil. Move the magnet away from the coil. The galvanometer deflects, but in the opposite direction, meaning that current is set up in the opposite direction. If you move the magnet with the south pole facing the coil and repeat the steps, the deflections occur but are reversed. What if the magnet is held stationary? No deflection. This is very important, that current is only induced if there is relative motion of the coil and magnet. Only when the magnet is moving is there deflection. But when it stops, the galvanometer pointer comes back to 0. The current produced by the relative motion of the coil and magnet is called an induced current and is set up by an induced EMF. The production of an induced EMF in a conductor in a closed circuit by the relative motion of a magnet and a conductor is called electromagnetic induction. So what explanation can one give for this? These represent a neutral atom and electrical balance. An outside force can break an electron away from an atom and start an electron chain reaction, an electric current flow. One way to provide that outside force is by use of magnets. It was proven in Form 2 that a magnet has lines of force which connects its poles. For simplicity, let us consider the effect of this magnetic field on a single electrically neutral atom. Now we move the magnet so that the magnetic field will strike the atom, supplying energy which forces the electrons to leave the atom and become a free electron. The result is a sort of electron chain reaction. In a conductor, electrons are normally moving in all directions. But when a magnetic field is passed through the wire, several electrons are forced from their atoms and move in one direction. In studying electricity, we are mainly interested in the movement of free electrons. So for convenience, let us look only at the action of electrons in a conductor. When the magnetic field sweeps down across the conductor, electrons move in one direction. When the field sweeps up across the conductor, the electrons move in the opposite direction. This movement of electrons in either direction gives rise to an electric current flow. If we move the field more slowly across the conductor, fewer electrons are affected in a given period of time and the current flow is decreased. And when we stop moving the magnetic field, the current flow stops and the electrons once again move in all directions. So if this wire is connected to a meter, we find that there is no current flow. When the magnetic field is moved down, there is flow of current in one direction. If the field is moved up, current flow is in the opposite direction. We can change the amount of current flow in several ways. Move the magnet faster, more current flow. Use a stronger magnetic field, still more current flow. Now coil the wire so that several turns are in the path of the magnetic field. Again, the current flow is increased. Stop moving the magnet, current flow stops. And so the principle of induction involves moving a magnetic field across a conductor. If you move the magnet across the wire, some electrons move. Move the magnet away and the electrons move in the opposite direction. If you move the magnet faster, more electrons move. So the faster you move the magnet, the greater the current flow. Key point to note is that a moving magnetic field causes electrons to move. In other words, a changing magnetic field can generate current. So what factors affect the magnitude of the induced current, or EMF if you like? You can actually find out this experimentally in a lab. We have an ammeter here and we have 3 coils. A coil with 1 loop, 10 loops and 100 loops. We also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. Now we have the single loop connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a very slight deflection of the ammeter needle. Now let me connect the 10 loops coil. And I'm going to do the same thing. I'm going to move the bar magnet in and out of the loop. Now you can see more deflection of the needle. In fact, if I go very slowly, you see just a little bit of deflection. And if I go quickly, a greater amount of deflection. So as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there is no deflection, no current flowing. So when the magnetic field is going into the coil, there is a positive current flowing. When changing, coming out of the coil, there is a negative current flow. And finally, we go to the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right. Pull out to the left. Go in quickly. You see a much greater deflection. Okay? So the rate of change of the magnetic field affects the current also. So these are the observations we've made. 1. that the amount of induced current increases as the number of turns increase. And this has everything to do with the length of the wire within the magnetic field. 2. That the amount of induced current increases with increase in the strength of the magnetic field. This strength of the magnetic field is called the magnetic flux. Thirdly and finally, that a larger current is induced when the magnet is moved in and out quickly. When there is no magnetic field in a region, the magnetic flux is zero. As you move in a magnet, the magnetic flux increases from zero to a maximum. Again, if you pull out the magnetic flux decreases from a maximum to zero. This change is called the magnetic flux change. The larger the change, the larger the amount of induced current. This is the Faraday's law of electromagnetism, which states that the magnitude of an induced EMF is directly proportional to the rate of change of magnetic flux linkage. We need to discuss another law called Lenz's law, and to understand it, 2 quick things to remember. You and I know that a current-carrying conductor has a magnetic field around it. And here again we are saying that if we bring a magnetic field near a conductor, we induce current in the conductor. So then it will mean that if we induce current in a conductor, at that very instant when the current flows in the conductor, that conductor also creates a magnetic field around itself. And so at that instant, when the current is induced, we shall have 2 magnetic fields, one from our bar magnet and the other from the conductor. That makes sense now, right? Good. The interaction of these 2 magnetic fields is the basis of Lenz's law. Lenz's law states that the direction of induced EMF is such that the induced current, which it causes to flow, produces a magnetic effect that opposes the very change producing it. What that simply means is that as you move the magnet towards the coil becomes an electromagnet with polarities so as to offer repulsion. So if you are pointing the North Pole, the electromagnet at that end of the coil will be a North Pole so that it opposes that movement. Again, as you pull the magnet away, the polarity at that end changes so as to attract the bar magnet, so that again there is opposition to that move. So if you're pulling away a North Pole, that end of the electromagnet becomes a South Pole so as to attract the North Pole of your magnet. Remember, the polarity of an electromagnet is determined by the direction of flow of current in the coil. Conventionally, if you consider one end of an electromagnet and the current flow is clockwise, that is the South Pole. If anti-clockwise, that is the North Pole. So using Lenz's law, we can be able to tell the direction of the induced current. What about a straight conductor? How do you tell the direction of current flow? The direction of induced current in a straight wire can be worked out by using Fleming's right-hand rule. The thumb and the first finger of the right hand are held at right angles to each other, and with the first finger pointing in the direction of the field and the thumb in the direction of motion, then the second finger points in the direction of the induced current. On your screen is a solenoid coil connected to a galvanometer. Movement of the solenoid causes the galvanometer to deflect towards the right. What direction is the solenoid moving? Note that the galvanometer needle tips towards the incoming current. Pause the video and think it over. Let us now work it out. If the galvanometer needle tips to the right, it means current enters through the blue terminal and leaves through the red, back to the solenoid, and the cycle continues. So at the end near the magnet, considering the winding of the wire, current flow is anti-clockwise. So that's the north pole of the electromagnet. Two north poles near each other causes repulsion. According to Lenz's law, it follows that the solenoid was moving towards the right, so that a repulsive force is created to oppose that motion. So that now we look at mutual induction. Mutual induction is said to occur when a changing current in one coil induces a current in another placed close to it. The changing magnetic flux in the first coil, called the primary coil, links with the second coil, called the secondary coil, inducing an EMF in it. To understand mutual induction, let us consider the magnetic field in a conductor once again. When we pass current through a wire, the red arrows indicate increasing current flow. A magnetic field is formed. To get a stronger magnetic field, we increase current. Alternatively, what we can do is use two wires. Doubling the wires doubles the effect of current passing a certain point, and therefore it doubles the magnetic field strength. We can create stronger magnetic field by using a coil. We're basically using the same principle of many wires to increase the strength of the magnetic field. By looping a wire into a coil, the same current carrying conductor passes through a point repeatedly. Magnetic field around each wire effectively adds together and makes a very strong magnet. So if you consider this coil and once again think of the cross-section of the wire at one section going into and the other out of the page, the dot is the current towards you and the cross is current away from you. That is the magnetic field around each section of that conductor. The magnetic field actually adds together, creating one large magnetic field, and we can represent this using field lines, showing the combined magnetic field. What we can then do is wrap this coil around an iron core. When we do this, because magnetism passes through a wire much faster than air, we find the field is constrained within the iron core. It permeates the iron core, meaning it basically travels through the core. Iron can be several thousand times better conductor of magnetic field than air. And so we can introduce a secondary coil, and you see how the magnetic field travels through that secondary coil. So what will happen is induction in the secondary coil. Important to note is that the magnetic field has to be changing in order to induce current. Look at the primary coil. Red arrows indicate the size of current, bigger arrow, bigger current. Increase the voltage, current increases, and we get a growing magnetic field. But once current is the same, the magnetic field is static. Look at that again. Increase voltage, increase in current, change in magnetic field. Voltage stays the same, current stays the same, magnetic field stays the same. The idea is voltage is only induced in the secondary coil when the magnetic field is changing. So as long as the magnetic field is changing, we have voltage in the secondary coil. But once it stays the same, there is no voltage induced. Watch that again. Change in magnetic field, we have a voltage in the secondary coil. But when there is no change in magnetic field, we have no voltage. So what's needed is an input voltage that changes continuously. and we can get this by using a sine wave. You see, the sine wave constantly changes the voltage, which causes change in the magnetic field, which means that we are always going to have a voltage in the secondary coil. So induced voltage depends on the strength of the magnetic field and also the number of turns on the secondary coil. More turns in the secondary coil will generate more voltage, and this is applied in the construction of transformers. Transformers are composed of an iron core or ring wrapped in coils. One coil is connected to an AC input voltage and is the primary coil. The other coil is connected to an output circuit with a load and is called the secondary coil. The two coils are well insulated from each other and have no physical electrical connection. This gives the transformer its unique electrical altering properties. Transformers can either step up or step down electrical voltage. In a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. The constantly changing current driven by an alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage in the load or resistance in the secondary circuit. If there are fewer turns in the secondary than in the primary coil, this is a step-down transformer. The resulting voltage in the secondary circuit will be less than in the primary. In this example, we have 20 turns in the primary coil and 10 turns in the secondary. To determine the decrease in voltage occurring in this step-down transformer, we use a simple transformer formula. Simply stated, secondary voltage to primary voltage ratio equals to secondary coil to primary coil turn ratio. Rearranging the formula and dividing 10 turns by 20 turns, we get 0.5 times 120 volts. This gives a step-down voltage of 60 volts. Generators. A generator converts mechanical energy into electrical energy. A generator works on the principle of electromagnetic induction. An AC generator has an armature ABCD, which is a rectangular coil of many turns wound around a soft iron core. A shaft that can be rotated rapidly, a field magnet, which is a strong field magnet with concave poles, two slip rings S1 and S2 connected to the armature and thus rotate with it, two brushes B1 and B2 which provide electrical contact with the slip rings, and a load which may be a galvanometer. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and the slip rings and the brushes. Note that the galvanometer swings between the negative and positive value. This means that an alternating current is flowing through the galvanometer. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So the current will flow from B1 to B2 through the galvanometer. During the next half rotation, arm AB moves up while arm CD moves down. Again, by Fleming's right-hand rule, current will flow in the direction ABCD. That is from B2 to B1 through the galvanometer. Therefore, the induced current changes its direction every half rotation. Suppose the armature takes t seconds to complete one rotation clockwise. At time t equals 0 seconds, the armature ABCD is vertical with the arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily 0. Hence, the induced EMF at this position is 0. During the first quarter rotation, the induced EMF increases. Then at a quarter t seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux momentarily attains the maximum value. Thus, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then at time a half t seconds, the armature again becomes vertical and the induced EMF is 0. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time 3/4 t seconds, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes 0 momentarily at time t seconds as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal. The DC generator works on the same principle but differs a little in construction. There is a horseshoe magnet with concave poles and a rectangular armature coil. Rotation of the armature is perpendicular to the direction of the magnetic field. A split ring commutator is attached to the ends of the coil like this instead of slip rings. Two graphite rods called brushes are in contact with the slit ring commutator. The brushes are fixed and are connected to an external circuit. Suppose the coil is rotated anti-clockwise. The red part moves up and the blue part moves down. Applying Fleming's right-hand rule, we get the direction of induced current like this. For the blue part, the direction of the induced current is this. So the induced current in the external circuit is this. This direction remains the same as long as the red portion is moving up and the blue part is moving down. When the coil crosses this vertical position, the blue part touches this brush, and the red part of the split ring touches this brush. This is just the opposite of what happened in the previous cycle. Now the blue part moves up and the red part moves down. Applying Fleming's right-hand rule to these parts, we get the direction of current like this. We see that the direction of current in the external circuit remains the same for this half rotation as well. So the current does not alternate and is said to be direct.